All right. So for today, we will be doing lesson 1.2 limits and continuity. So I assume you have watched the corresponding lecture videos from the YouTube channel of iMath. So for today, I'll just be doing some examples that I have prepared in here. So let's get started. So first problem here, evaluate the following limit if it exists or show that it does not. So in this type of problem, um, well, I did not give any hint whether the limit exists or not. So at the very beginning, you might want to, you know, test some curves passing through the point here and show if if you can find some uh differentiating limits, or if you can easily observe the function here, that you can simplify it so that things can get easier, then try to do that. First, you have to take note that as the point xy goes to the point 1 comma 0, this function here, this actually goes to 0 over 0. So this is an indeterminate form. So you can check that. You see, you will have 1 minus 0 minus 1 over here. You have 0 plus 0. So this is 0 over 0. So this is an indeterminate form limit, right? So in this case, maybe you can manipulate the expression, manipulate this function here, that maybe you can cancel some expressions that make these expressions here 0 over 0, okay? And if that's possible, then maybe you can find the limit. Maybe the limit exists. So the same technique that you actually use when you were dealing with functions with a single variable during your Cal 1. So anyway, what can we do? Maybe in here in the numerator, if you look at this, x can be factored out. Maybe that's, that would be um, one of the steps that we need. And then if you look at this is just a radical expression. So maybe we can multiply and divide the whole expression by the what I call radical conjugate, meaning if this is a plus, then we can multiply and divide it by the same expressions that we see here, this guy and this guy, but this one here is minus. Let's start with that. So we can multiply and divide the whole expression by square root of x minus 1 minus y divided by square root of x minus 1 minus y. Therefore, this guy here, we will have the limit as xy goes to 1 comma 0. Here, we factor out x. Let's do that. If we factor out x, we will have x times x minus y squared minus 1. And then here, let's just retain this factor. This is square root of x minus 1 minus y. On the denominator, notice that this guy here, this is just expression that will give difference of two squares, because one of them is plus, the other one here is minus. So that if we do the multiplication, we will end up with x minus 1 minus y squared. Okay? And now we clearly see that this guy here, x minus 1 minus y squared, will actually cancel this. X minus y squared minus 1. So now this simplifies. So this limit simplifies into the limit as the point x comma y goes to 1 comma 0 of x times square root of x minus 1 minus y. Alright? So if we evaluate, take note that this is no longer indeterminate form, and in fact, we can get some limit. To evaluate this at the point 1 comma 0, we will just have 1 times, here we have square root of 1 minus 1 minus 0. So the limit will be equal to 0. Okay? So the limit exists and the limit is equal to 0. Any questions? So as you can see, the technique that we just used here, it's a similar technique that we do if we find indeterminate forms of type 0 over 0 when we were discussing functions of one variable. So similar technique. All right. So let's get the next number here. Evaluate the following limit if it exists or show that it does not. So in here, we want to find the limit as the point x, y goes to 0, 0 of x minus y squared all over x squared plus y to the 4th. Now, what is your guess? Does the limit exist or does it not exist? I got one answer here. It says does not exist. In fact, it does not exist. So showing that the limit does not exist, one way is to find several curves passing through the point a comma b or x naught comma y naught. In our case, this is 0 over 0 comma 0. So we want to find, two curves. We want to use two curves passing through the point 0, 0 and show that along those curves, the limit of this expression here are different. And once we have that, then we can easily conclude that the limit does not exist. So let's see. Normally we can try, x goes to 0 or along the curve, normally we use the easiest curves. So along C1, maybe x equals 0. So we fix x equals 0 and we let y, just move so that it goes to 0. Or maybe along C2, and here we fix y equals 0 and then we just let our x go to 0. Right? So if we actually do these two curves, you can try. If we actually use these two curves, then the limits will be the same. Okay? So maybe let's try that along C1, which means x equals 0. So the limit here, limit x comma y goes to 0 comma 0 of x minus y squared, quantity squared, over x squared plus y to the 4. This becomes, or this simplifies into the limit as y goes to 0 of 0 minus y squared over 0 plus y to the 4. But this one here, it's just what? We have the limit as y goes to 0 of y to the 4 over y to the 4. So in here, these two guys cancel, so it's just equal to 1. So the limit here equals 1. Okay? Now, if we do along C2, okay, if we do along C2, we actually hope that the limit is not 1. And if that's the case, then the limit does not exist. But if it is equal to 1, then we have to try another curve. Okay, so there's a comment, -1. It's not -1. Remember, although there's a negative in here, you square it, the negative disappears. Okay? So yes, there is negative y squared here, but take note the whole thing here is being squared. So becomes positive y to the 4. So yeah. So anyway, along C2, we will have the limit as the point x comma y goes to 0 comma 0 of the same expression. We have x minus y squared over x squared plus y to the 4. So it will simplify into the limit as x goes to 0 of x minus 0 squared over x squared plus y to the 4. And again, so this becomes 0 to the 4. Let me write that. So this is just the limit as x goes to 0 of x squared over x squared. And just like before, these two guys will cancel. So the limit is equal to 1. So the limits, they're the same. And well, we need to find another curve where this function goes to maybe a different limit. Okay. I remember someone asked me, when do we stop? When do we stop checking curves? To answer that question, actually, you don't know. There's no general rule as to when you will stop checking curves. Okay? Maybe you're just not lucky that you were choosing curves where the function where along that curve the function goes to the same limits. Okay? So there's no general rule. You just need some practice and maybe familiarization on how to deal with such expressions, or which curves are obviously giving different limits. Okay. All right. My question here, may hint po ba para malaman if D and E yung limit? Actually, wala akong masabing hint. Okay? It really boils down to familiarization of, expressions. Normally, we give similar expressions. So, yeah, if you just practice a lot of expressions, a lot of limit problems, then maybe you'll encounter the same problem in the future. So you would know that, oh, the limit does not exist. Oh, the limit will exist. So personally, even for me, I won't see immediately if the limit exists or not. I have to compute that. Right? So if you can have some, if you can give some light as to when the limit exists or does not exist, then share it with us. So, but like I said, personally, ako, hindi ko kagad mapapansin ko yung nag-exist yung limit or hindi. So, ganun din ako. Magta-try and error din ako. Magta-trial and error din ako until I find maybe the limit really exists. Maybe I'm just using a different curve. So, yun. Ganun sa akin if I were to ask. Okay? All right. So, let's see. Let's try a different curve. Okay? So, I'm thinking of a curve. So, maybe you can also think of a different curve. If at this point you have already thought of a different curve, you can share it. What I'm thinking is, so one suggestion here says x equals y. So x equals y, that could probably work. So let's try that. So one suggestion was x equals y equals x, or whatever. So say along C3, which is x equals y or y equals x. Okay? So in this case, let me label this as capital L. So capital L, it will reduce to what? So x equals y. So let's say we replace all the y's with x. We replace all the y's with x. You will have x goes to 0 of what? We will have x minus x squared, quantity squared, divided by x squared plus x to the 4. Okay? And then let us simplify this limit as x goes to 0 in this expression here. We can factor out x. So you will have x times 1 minus x, and then there's a square outside here. On this part here, we can factor out what? X squared. So if we factor out x squared, what's left is 1 plus x squared, correct? But in here, if you distribute this squared over this product here, this guy will cancel this guy. So that you will actually get the limit as x goes to 0 of 1 minus x quantity squared over 1 plus x squared. And notice, as x goes to 0, the limit is still equal to 1. It's a good try. X equals y. But the limit is still 1, so we can't conclude anything with this. Okay. Now, I say it's a good try because you know that the curve you are using, it will pass through the point 0, 0. There are some students who will just, you will just give curves. Will just think of curves, but the curve does not pass through this point here. Okay? And definitely, if you have tested those curves, you will find a different limit. That's because it does not pass here. The curve does not pass on the point AB or on the point x naught comma y naught. So they thought that the limit does not exist when in fact, possibly the limit exists. It's just that they are thinking of a curve that is not really valid to use. right? So I'm saying that for those who said or who suggested x equals y, it's a valid curve because, well, it passed, the curve passes through the point 0, comma 0. So it's a good try, right? So it's a good try, but um, not the one we need. So other trials there. Well, if y equals x or x equals y does not work, then maybe we can increase the power a bit. So for example, um, this is equal to L. So maybe we can try x equals y squared. X equals y squared. So look at this. Along C, we're on C4 now, right? Along C4, x equals y squared. So for any point A, B, satisfying x equals y squared, the x is equal to y squared, right? So you have ordered pairs A comma B, and it is on this curve, then the A, it will be equal to B squared, okay? So we have L. Take note, your x is equal to y squared. So we are what? We are replacing x with y squared. So we can now say let y go to 0, and it's the same thing as the x comma y goes to 0 comma 0. So limit L, it's equal to the following. The limit of quantity, your x becomes y squared minus y squared. Outside, it's, quantity y squared. And then here you have y squared because you have x squared there, plus y to the 4. And now, notice, your x is always equal to y squared. So what happens here? Y squared minus y squared, that's constant 0. So the limit as y goes to 0, the numerator is always 0, while the denominator, it's not equal to 0. It's actually 2y to the 4. So numerator is constant 0, denominator, it's non-zero, it just goes to 0. This means the limit here is equal to 0. And voila, we found a curve in which the function goes to a different limit. So now we can conclude. Therefore, so here 0 not equal to 1 as in the previous solution. Therefore, limit does not exist. Limit does not exist. Okay. Questions? All right. So let's check our next item. Evaluate the following limit if it exists or show that it does not. So here, limit of x minus y squared minus 2y minus 3 all over y squared of x minus 2 plus y squared. As the point xy goes to 2, negative 1. Okay, so here we can check direct substitution. You will have here 2 minus negative 1 squared minus 2 times negative 1 minus 3 over, you have here negative 1 times square root of 2 minus 2 plus -1 plus -1 squared. Check that this is actually 0 over 0. So this is indeterminate. Okay, this is indeterminate. So the limit may or may not exist, but what is your wild guess? What is your wild guess? Limit exists? So, wild guess is, so someone said limit exists. Let us check. So if the limit exists, then we have to show that indeed it exists via what? Laws about limits, or limit laws, or limit theorems, or maybe the definition. Normally we don't do definition, okay? At least at our level. The definition, sometimes it's a tedious work if we prove limits by definition, especially if if we are dealing with two or more variables. So let us avoid definition first. Let us check, however, if we can use some limit laws. Maybe we can simplify this expression. Maybe, just maybe. So how are we going to do this? So we already know that this is 0 over 0. Now, if we look at this, y is factorable. So y is factorable. Maybe we can factor out y. We can factor out y. And then let's do some grouping. Okay, let's do some grouping. Notice that for this expression, after we factor y, so that expression, we can write it as y times square root of x minus 2 plus quantity 1 minus, or 1 plus y. Correct? That expression on the denominator. And if you remember our first problem, the first problem that we solved, we multiply and divide by the radical conjugate. So maybe we can use that same technique here. Okay? So, that case, let us try that. So we multiply and divide by the conjugate of this. So it's square root of x minus 2 plus 1 plus y divided by square root of x minus 2 plus 1 plus y. So the limit becomes limit as the point x comma y goes to 2 comma -1. The numerator, let's retain that. Let's retain that as x minus y squared minus 2y minus 3. And then here we have the expression x minus 2 plus 1 plus y. On the denominator, remember that we have factored y in here. We have factored y in here. So there is a comment, and that's correct. Since this is plus, this should be minus. Thank you. So that should be minus. So this is minus, and this guy here is also minus. Thank you. And then now, So remember, there's a factor y here, and then this guy multiplied to this expression. Again, difference of two squares. So you will have x minus 2 minus quantity of 1 plus y quantity squared. Correct? Now let's try to expand this, and I hope after we expanded that, some nice things will come out. So we have the limit x comma y goes to 2 comma negative 1. The numerator is still the same, x minus y squared minus 2y minus 3 times square root of x minus 2 minus 1 plus y. In the denominator, we still have the y outside. Then we have x minus 2, then minus, we expand 1 plus y squared. It's 1 plus 2y plus y squared. And then we distribute this negative. So we will have limit x comma y goes to 2 comma negative 1. Still on the numerator, we have x minus y squared minus 2y minus 3 times square root of x minus 2 minus 1 plus y divided by, we have here y times, we have an x, then minus 2 minus 1, here we have minus 3. Then here minus, also this one minus, so minus 2y minus y squared. And voila, we have this expression cancels this expression. And now it's no longer indeterminate, and we can actually get a value. So as xy goes to 2 comma negative 1, in the numerator, we will have square root of 2 minus 2 minus quantity 1 minus 1. Numerator is 0, denominator is just negative 1. And yep, this is equal to 0. So indeed, nice guess, nice work. The limit is equal to 0. Okay. Any questions? For our next problem, evaluate the limit if it exists or show that it does not. So in here, limit of x squared y over x over 2x cubed plus 5y squared as the point x, y goes to 0, 0. So you can easily see that this is 0 over 0 indeterminate form. So we need to use either, we need to use limit laws or definition if the limit exists, or maybe we can find at least two curves where the limit will be different for the curves. But what do you think? Exists, does not exist? So some said it exists, some said find curves. Yeah, maybe we can actually find curves. The limit here does not exist. So our goal is to find curves where, of course, the curve passes through the point 0, 0, and that using a different curve the limits will be different. Let's see. I hope you would see that obviously if you use the curve x equals 0 or y equals 0, you will get the same limit. Well, at the very least, I hope you would see that one. So that said, just use one of them. Just use one of them. So let's say along x equals 0. So I'll put this guy here as, say, L. So L equals, now along x equals 0, so we just let y goes to 0. But in the numerator, it's just completely 0. While on the denominator, it's 0 plus 5y squared. So denominator is non-zero. So the limit here equals 0. Now, for those who commented or who said in the chat room that we find curves, can you give a curve that will give a different limit? So say along what do you think? Maybe we can use what function? Yeah, y equals x maybe. Let us try. Y equals x. So L equals, we say limit as x goes to 0. So we are replacing all the y's with x. So this will be x squared times x divided by 2x cubed plus 5x squared squared. 5x squared. And what is this? If you notice, in the numerator, we have limit x goes to 0. In the numerator, we have x cubed. On the denominator, we will have, we can factor out x squared first here in the inside. So you will have x squared, and then we have here 2x plus 5. And then very outside, we have x squared here. So here, we will have limit x goes to 0. And notice, in the numerator, that's x cubed, while on the denominator, we have here x squared, and that is also being squared. Yeah, that is also being squared, which means we have here 1 over x times 2x plus 5 quantity squared. Take note that this guy here, it does not have the square anymore. And therefore, this does not exist. As x goes to 0, this does not exist. Could be either plus infinity or minus infinity, depending on where the 0 is coming from, either from the left of 0. Sorry, depending on where the x is coming from, either from the left of 0, from the right of 0. So here the limit does not exist, which, well, that's a very good one. Therefore, yeah, limit does not exist. Does not exist. Oops. Okay. Questions? Okay. So for the next problem, this will be the last problem that I'm gonna do. Let f be this function. It's a piecewise function. Show that f is continuous at the point x comma y equals 0 comma 0. So how do we do this? Similar, maybe we can do similar, or we can use similar characterization from Cal 1, definition of continuous function. There is a limit, there's a functional value, and they are equal. Okay? So there's a limit, there's a functional value, and they are equal. So let's test that. Obviously, we have a functional value, f of 0, comma 0. This is just equal to 1. This is just equal to 1. And then we find the limit. Limit of f of x, comma y as x comma y goes to 0, 0. We want to show that this is equal to 1. So based on the piecewise function, based on the definition, we have the limit as the point x comma y goes to 0, comma 0 of sine x squared plus y squared over x squared plus y squared. If you remember the following, this could give you a hint. Remember, limit as x goes to 0 of sine x over x, this is equal to 1. And look, it's very much the same. You have your x squared plus y squared as the argument in sine. The denominator is also x squared plus y squared. And this guy here, this goes to 0, comma 0. So you just need, because in here we are dealing with a single variable. So in order for us to use this, to be able to use this, maybe we can rewrite this expression as a single variable, which is easy. Just maybe you can convert this to polar form. If you convert this to polar form, let's see, you can have x equals r cosine theta, y equals r sine theta, so that x squared plus y squared, this is equal to r squared. Yeah. And in here, as the point x comma y goes to 0, comma 0, the r also goes to 0. So we're almost there. In fact, not just r, but also r squared going to 0. Right? Which means after conversion, we can rewrite the limit as r, or r squared goes to 0 of sine r squared divided by r squared. And now we can use this. We can use this hint here. Okay? If you want to be more accurate, you can put r squared here because that's actually this part here. Okay? So here we can see that the limit is actually equal to 1. And yay. So this means that f of 0, comma 0, this is also equal to the limit of f of x, comma y as x, comma y goes to 0, comma 0. Therefore, f is continuous at 0, comma 0. Okay? Any questions? So there's a question. This is a very good question. Pwede po bang gamitin na lang yung curve x equals y instead po na mag-polar? That's a very good question. Now, you see, for example, if you're on this domain, okay, the domain in your functions of two variables, it's a planar, it's a plane or possibly, a disk or whatever. This is the point. Say this is your point A, comma B, or x naught, comma y naught. If you use your point x, comma y, you are only considering, say, this guy here, that single line. But when you want to find limits and the limit exists, okay, you have to find all possible lines. Correct? You have to find all other curves, say something like this, or maybe something like this, or maybe something like this. So you just tested one curve, x equals y, if you do that. Okay? But not all possible curves. Okay? Now, what about this? What about this? When you convert Cartesian to polar, you are not actually changing any of the curve. You are just changing your plane. How you look at the plane. Before you look at, you know, uh, things or objects in the Cartesian planes as squares, correct? In the Cartesian plane, you look at the grid that looks something like, let me write it here. In the Cartesian plane, you look at grids, correct? Okay, so if you have a point, say in here, that's a point that you can represent in a grid. On the other hand, if you convert things in polar, then instead of looking at grids, you are looking at circles. But they're the same. I mean, you are on the same plane, but looking at a different point of view. Therefore, when you convert from rectangular to polar, and you do this conversion, then you are considering all points. You are considering all possible curves that passes through that point. Because, like I said, when you convert, the point can be represented in terms of a radius and an angle. Okay? Is that clear? So, my method to solve po ba siya if di namin makita yung hint or polar conversion? Possibly meron. Possibly meron. But the easier way would be polar, at least in this particular example. You can solve this in a different way, possibly, but converting it to polar form, it is easier to do. Yeah? Sir, kailangan po ba dumaan sa polar knowing that the limit of sine x? Yeah, yes, you know that the limit of sine x over x equals 1 as x approaches 0. But this is as x approaches 0. This is what? This is single values. Okay? I mean single values, single variables. Okay? But we don't know for multiple variables. Well, somehow, yes, it will be the same. But the theorem that we know so far, or at least the theorem that we are familiar with, is when we are dealing with single variable, with one variable only. Okay? Other questions? So if none, anyway, it's almost time. Thank you for coming. So for tomorrow, please check the next lecture. It will be section 1.3. And yeah, that's all from me for today. Thank you.